Ibu, you want to start already?
Yes, let's get going. Okay, so today we are happy to have Eric Perlmutter from Laplace. It's really great to have you. Please take it away.
Thanks, Ibu. I'm very happy to be here at QFT and Geometry University. It's an honor to give a talk as part of this series. So thank you for the invitation. I will be talking about this paper with Scott Collier that came out in January. And it's about the intersection of a couple topics. Let me give a bit of a mini introduction as to where the talk will go, and then we'll dive in. Okay, so the talk is about S-Duality and n=4 super Yang-Mills, and holography and their entwinement. So to basically quote from the beginning of our paper, there are two goals. The first is field theoretic, to understand how to extract the full physical implications of S-Duality for the observables of n=4 super Yang-Mills and ultimately other SCFTs with S-Duality symmetries. And second, to put this in the context of the ADS-CFT correspondence between n=4 and string theory and ADS5 times S5 by applying what we learned from treating S-Duality in a new way. So what do we need to know about n=4 to understand what I'm going to try to say? n=4 super Yang-Mills, the gauge theory, contains a complexified gauge coupling, tau, which is written in terms of the theta angle and G Yang-Mills in this usual way. And I will refer to G Yang-Mills as just G. Being exactly marginal, tau parameterizes a conformal manifold. The n=4 preserving conformal manifold is one complex dimensional parameterized by tau. And I've drawn it here as this teardrop region where the point at the top is meant to be the cusp where the free theory lives at large imaginary tau. n=4 super Yang-Mills is believed to enjoy S-duality. And for a simply laced gauge group G, this is up to global identifications, a self-duality under SL2Z transformations of tau. I don't have to tell this crowd that if you need to or want to study all the observables in the theory, and extended objects and so on, the global identifications are important. But for what I'll talk about today, we'll be focusing on the SL2Z invariant sector of the theory. And the existence of this symmetry is, in my opinion, beyond a reasonable doubt, which is the starting point for the project. So what is the evidence in favor? Well, on the field theory side, there are lots of different types of calculations involving instantons. Some are at large n, some are not. And in the context of ADS-CFT, with string theory in the bulk, well, string theory in 10 flat dimensions enjoys its own SL2Z symmetry acting on the complexified string coupling. And the ADS5 times S5 compactification preserves that symmetry. The duality has checked this, the holographic duality has checked S-duality in various ways. For example, by noting the S-duality invariance of certain terms in the low energy effective action, or doing certain detailed matching between instanton computations in the bulk and on the boundary. We'll be concerned with non-perturbatively well-defined observables, which I'll call O of tau, which obey the invariance under SL2Z transformation of tau. So this class of observables includes things like conformal dimensions, OPE coefficients, correlation functions of short operators. And as I alluded to before, there are some things that are not strictly SL2Z invariant. They may be invariant under congruent subgroups. Those are things like line operators. But today we'll be focusing on this very wide class of observables, which is central to defining the theory in the first place. And I'll call these O of tau. O is an observable, it's not an operator. And despite appearances, everything I'm talking about today depends non-holomorphically on tau, but I'm just writing things as a function of tau and rather than tau and tau bar to save space. So the question we want to understand can be phrased as asking, what is the explicit modular structure of these observables? And this is perhaps obviously a hard problem. So to give two angles on why this is a hard problem, the first is that S-duality is inherently non-perturbative. So it's a strong weak coupling duality. And so to get control over the functional dependence on tau of some observable O, you need to understand that observable in regions of intermediate coupling where G is of order 1, and that's hard. In the 't Hooft limit, where integrability rules, S-duality is obscured. as we'll discuss later, it's not that it doesn't apply, it's just that it's obscured by the limit one takes in which G is double scaled to 0 as n is taken to infinity. You might ask, well, can't the conformal bootstrap do non-perturbative things? And of course, the answer is yes, but it's still hard to understand the functional form of an observable, for example, by staring at a numerical plot. Without some guidance in the world of possible SL2Z invariant functions, one struggles to draw the line between bootstrap constraints and this explicit functional form. So to summarize, I would say that n equals 4 super Yang-Mills has a symmetry that we've not fully used. And one answer as to what it means to use it is to bake it into calculations from the beginning, which reduces the observables to their dynamical content, which is not in part determined by the symmetry of the theory. So the idea that we're going to introduce to try to achieve this is to apply SL2Z spectral theory, which is to say, harmonic analysis on the modular surface, the fundamental domain of SL2Z. This is a tool the mathematicians have studied and is well established. And we're going to port it over to this context, and we'll find that it's a very robust tool that applies for finite n and for any such S-duality invariant observable. And one of the messages that I want to come across loud and clear in the talk is that it gives a very different looking presentation of a well-studied theory. And as far as we can tell so far, a lot of output from just a little bit of input. So we'll get some interesting results from doing rather elementary calculations once everything's in place. And so the message that I want to get across is that we should explore what else this tool has in store. Now, if we think about the large n limit and expand the n equals 4 super Yang-Mills theory around strong Tuft coupling, it's famously dual to type 2B string theory in ideas fashions S5 in the supergravity limit with a prescribed set of stringy corrections. And we'll find that this spectral decomposition point of view actually reveals that there's an emergent ensemble average within this duality. And it can be phrased as follows, to be substantiated later. The large n limit of the ensemble averaged n equals 4 theory is the strong coupling limit of planar n equals 4, that is to say, the ADS5 times S5 supergravity. And by ensemble averaged, I mean an average over this n equals 4 preserving conformal manifold parameterized by tau. This picture is meant to be a schematic of this relationship. On the right is the conformal manifold with this shading, and the shading is meant to indicate an ensemble average. And you take that average and you take the large n limit. And on the left is meant to indicate the strongly Tuft coupled theory. So you go to the cusp as you take the double scaling limit, and then you take large lambda. So this left figure is meant in the large lambda, large n sense. So it takes that, I want you to interpret it that way. And we'll talk more about this later, of course. This correspondence relates to various other themes in ADS CFT recently involving factorization and wormholes, and generally promotes the study of what we call the SL2Z ensemble, which is the ensemble of n equals 4 theories. So we'll say some about this later, and I think there's really more to be said. So that's the executive sort of overview of the talk. Where is this going? So first I will introduce this spectral decomposition into SL2Z invariant eigenfunctions and explain how and why it applies in the n equals 4 context. This will reveal various interesting features of the observables in question, their analytic structure, and some redundancy of instanton physics in n equals 4 that seems very unobvious by other means. A lot of what we say was tested and can be nicely put on display for this integrated correlator that was studied recently by Doragoni, Green, and Wen. So we'll talk about that. In large n, we will go to the Tuft limit, see what this formalism is telling us, and then we'll transition to this ADS CFT story that I just alluded to and study this SL2Z ensemble a bit and make some general remarks about how this relates to wormhole physics and similar topics. Please interrupt with questions. Let me pause and ask if there are any now. And if you have one and I haven't paused, just feel free to speak up. Okay.
Can I ask a question?
Yeah, please.
So in this ensemble average, I thought n equals 4 Yang-Mills was one of the cases where it wasn't totally clear whether an ensemble was going to be generated, in part because you're averaging in some sense over the dilettante. And if you vary the dilettante, you might change the value of the bulk cosmological constant. Can you comment on this?
I'm not sure I have anything strong to say in that regard, but maybe we can return to that in the ensemble average part.
Okay.
Which will be later. Yeah.
Can I ask one more question on the
yeah,
ensemble that maybe you'll ask about? So this is going to apply for both high and low dimension operators. There's no distinction in the discussion, or?
Yeah, I appreciate the question. It's not totally clear. So what I mean by that equivalence applies to things that can be computed within supergravity. Now you might say, do you mean including the microstates of a black hole? And it's not totally clear that that is well defined, as was recently emphasized in the Schlenker-Witten paper. And I'll try to make some comments about the relation to that paper, but that'll be at the end too.
Okay, thanks.
Sure. Okay. So the basic fact that we're going to use is that a square integrable SL2Z invariant function admits unique decomposition into an SL2Z invariant eigenbasis, and it's an eigenbasis of the Laplacian on the upper half plane. Now here's what the decomposition looks like. We'll talk about these ingredients in turn. There are basically three pieces. The first is a constant as a function of tau. It's this O bar. That is what I've called the modular average, and that is essentially the integral of O over the fundamental domain. All inner products here are taken with respect to the Poincare metric, and so this first term is just the inner product of O with 1 normalized by the volume of the fundamental domain. The second piece is a continuous piece. The basis elements are the non-holomorphic Eisenstein series with index a half plus IT, where T is real. And the third piece is a sum over an infinite set of discrete eigenfunctions known as Moss cusp forms. Before giving more details, let me show you a picture of the various functions involved, just to give a flavor. So what is this a picture of? There are 4 curves. There's the red curve and then the others. So I've squared some of these eigenfunctions and taken their 0 modes. Okay, squaring them involves all the Fourier coefficients, so it's a sort of robust indicator of the features of these functions. And I've taken the 0 mode, so these are just functions of the imaginary part of tau. And sorry, before I go on, I should have emphasized my notation throughout this talk is that tau equals x plus iy. Okay, and so for orientation, y was 4 pi over g squared, so large Y is the perturbative small g Yang-Mills regime. Okay, so we're plotting this as a function of Y in the x-axis. So the red curve is the square of one of the Eisenstein series in this continuum, where I've just picked a parameter randomly, a half plus I. Okay, and notice it's a pretty smooth curve, basically featureless except for some funny stuff down at small y, where anyway the numerics become slightly less reliable. And the other 3 curves are plots of the squares of the 3 lowest Moss cusp forms projected to the 0 mode. And these curves, of course, look very different, not just from the red curve, but from each other. They have a sporadic set of extrema. The amplitudes of the extrema are seemingly random. The 3 curves, if you look closely, have no triple overlaps, which is indicative of what you'd expect for sort of chaotic functions on a 2-dimensional domain. And indeed, these functions exhibit a form of chaos known as arithmetic chaos, a feature which this plot intends to make plain. So let's talk a bit more about these functions now. So again, the constant is the modular average. That's simple. The Eisenstein series you may well be familiar with. These are eigenfunctions of the Laplacian delta tau with eigenvalue s times 1 minus s. And here S is a half plus IT. These admit a Fourier decomposition, which is rather straightforward. I've defined what's known as the completed Eisenstein series by multiplying the Eisenstein series by what's called the completed Riemann zeta function, which is defined here. So it's a zeta with a gamma and some power of pi. Okay. And the reason to do this is that this completed Eisenstein series, E star S, obeys a functional equation. It's invariant under S goes to 1 minus S, which is clearly visible in the 0 mode and is also true in the other modes. Notice that the 0 mode is just a sum of 2 powers, a y to the s and a y to the 1 minus s. And the non-zero mode is given by this Bessel function with some number theoretic Fourier coefficient. Now, compared to the previous slide, I've written the overlap in terms of this bracket. So I have to find this bracketed overlap, and that's just the inner product divided by the same completed Riemann zeta that we use to define the Eisenstein series here. Okay, and because E star obeys a functional equation, so does this overlap of these two functions. A key point about the overlap of some SL2C invariant function with the Eisenstein series is that it can be re-expressed as a Mellin integral of the zero mode of O. So given the zero mode, you can reconstruct the continuous part of this decomposition. That's important. Finally, the last part and the most mysterious part of this decomposition are these Moss-Cusp forms. These two are eigenfunctions. They're parameterized by what are known as spectral parameters, Tn. So n is just a label, and these t's are some increasing set, which is believed to be non-degenerate. And there's an infinite number of these functions. Their existence is not totally obvious because the fundamental domain is not compact. But remembering that it has finite volume, it turns out that that's sufficient to prove their existence, and they obey a Weil's law of growth at large eigenvalue on account of the finite volume. As mentioned before, these functions are chaotic. And one reflection of that is that these spectral parameters are known numerically in many, many thousands of cases, and in some cases to extreme precision, out to 1,000 digits, but not in a single case are they known explicitly. And the same is true for the Fourier coefficients. So this function in the Fourier decomposition shares some similarities with, but also has some differences with the Eisenstein series. Here's the decomposition. The obvious thing is that there's no zero mode. As a result, at large y, it decays exponentially. That you can read this off from the behavior of the Bessel function, but more physically, this function goes like q plus q bar, and q is e to the 2 pi I tau, and so at large y, that decays exponentially. So that's what it means to be a cusp form. But the other modes have the same structural feature as the Eisenstein series, except that the Fourier coefficients ak, this is just a normalization factor. The Fourier coefficients ak are, again, drawn from some unknown chaotic distribution. They're known very explicitly in many cases, but not analytically in a single case. At large eigenvalue, these functions are believed, conjectured, in some cases proven, to exhibit universal chaotic behaviors. There's this whole subject known as arithmetic chaos. There are various conjectures, all of which fall under the umbrella of something called the random wave conjecture. There's also something called the quantum unique ergodicity conjecture, and various others. And this is an interesting subject. Unfortunately, I won't have so much to say about the physics implications for n equals 4. What I want you to take from this slide, if nothing else, is that these functions exist, they're known to exist, and a lot is known about them. But a lot is also not known about them. So to give a demonstration of their sort of chaoticness and weirdness, again, here's a plot, a sort of density plot of one of the cusp forms with this value of the spectral parameter. I think red is max, black is min, could be the other way around, doesn't really matter. The point I want to make is just that the global maximum for this function in the fundamental domain is here, and the global minimum is here. And these are sort of random weird values from the point of view of functions we're familiar with. For example, the Eisenstein series has a max up here, right? It grows at large y, like a power law. This is written a large s. And the minimum is always here at the corner, okay, for all values of s greater than 1, real part of s greater than 1. But for these cusp forms, they're all over the place. If you change the spectral parameter a little bit, these points move around, okay. So this isn't really necessary, I realize, for what I'm going to say in the future, but it's just fun to look at this plot and get a feel for these functions. Okay, so back to n equals 4.
Eric, I have a question.
Yes. Mm-hmm.
Going back to your expansion of ES and phi,
yeah.
Is it obvious that if I look at the non-zero modes for ES, that necessarily does not have any overlap with the phi ends?
They in fact do, in the sense that these are restricted to s equals a half plus it, and here, they have the same. The eigenvalues sort of sit on top of the continuous series.
Okay.
Yes.
So the decomposition.
But you mean literally like the overlap is in the inner product, or just did you mean the overlap of the indices in the sense of
The overlap in a product, also in the indices.
Oh,
the
okay.
question really is whether those two terms are completely independent.
Yes.
Or-
So this is known to be a basis, literally,
Okay.
despite this overlapping of the spectral parameters.
Okay, thanks.
Yeah. Mhm. Okay, so what's the point with respect to n equals 4? So a well-defined observable in any CFT is finite for all values of the coupling modulo possible divergences at boundaries of moduli space. So here in n equals 4, the only boundary of the moduli space is the cusp, but the cusp is just the free theory, where the observables converge to their free values. And if you're studying something that somehow is ill-defined in that limit, then just subtract off the free value and study the remaining thing, which also will be SL2Z invariant. So therefore, n equals 4 super Yang-Mills observables O of tau admit a spectral decomposition because they're SL2Z invariant and they're square integrable by the argument I just gave. We'll actually see that applying this technology naturally subtracts the free value. That is to say, at large y, the leading term is 1 over y, aka g squared. And that's one of the main points of the talk. Okay, so this technology applies to these observables, and now let's ask what we can get from it. Now, before working too hard, it turns out that two interesting implications come, quote unquote, for free. The first is that instantons are redundant. So what do I mean by that? If you take the observable O and, the left-hand side should just be O of tau, not OK, and develop a Fourier decomposition. In the n equals 4 context, k is the instanton number, the total instanton number. So for example, in terms of q and q bar, you count the number of instantons, you count the number of anti-instantons, you take the absolute value of their difference, and that defines what I'm calling instanton number. Okay. So the kth mode is the function part of O projected to the k instanton sector. And the redundancy is that the k greater than 1 instanton sectors are uniquely determined by the k equals 0 and k equals 1 sectors. The proof of this is that the decomposition I gave can be inverted using an orthogonality relation for the Bessel function with imaginary index. What's the idea? Well, recall that the 0 mode determines the Eisenstein part of the decomposition and the constant. So given the 0 mode, you fix that whole piece, imagine subtracting it off. And given the k equals 1 mode, you can invert these Moss-Cusp forms form by form, because the Bessels form the functional dependence in the k equals 1 Fourier sector. This assumes that there's no degeneracy in the cuspidal eigenspectrum, which is not strictly proven, but is widely believed to hold for SL2Z. But as a physics statement, it looks a bit strange at first and very powerful. And I think both of those things are true. The second implication is that we can define the ensemble average over a general conformal manifold in some CFT as the integral of some object, some operator, say, which is a function of moduli x, against some measure on the conformal manifold M. And a natural measure is the Zamolodchikov measure, so I'm defining it that way. There are other choices, but suppose we define the ensemble average with respect to the Zamolodchikov measure, which is inherited from the matrix of 2-point functions of exactly marginal operators. Well, in n equals 4 super Yang-Mills, because of maximal supersymmetry, the Zamolodchikov metric is exactly equal to the Poincare metric, and therefore the ensemble average is equal to the modular average. So to be clear, I'm defining this bracketed O as the ensemble average. It's not an expectation value of an operator, it's ensemble average of an observable. Okay, and the point is that this is very simply given by the modular average of that thing. And because the modular average appears very cleanly in the spectral decomposition, we see that the same is true of the ensemble average, which is a fact that we'll make use of later. Okay. So to summarize this point of view, the essential content of n equals 4 super Yang-Mills observables lives in their spectral overlaps. If you imagine studying a 4-point function, well, this is a function of cross ratios u and v, and it will be a function of tau. In spectral space, it's characterized by the overlaps. These overlaps depend on u and v, and for example, in the Eisenstein sector on this S parameter, but they don't depend on tau, right? You've factorized the tau dependence, so to speak, into the basis element. So now we want to ask, given the physics problem at hand, how are the functional forms of these overlaps constrained? Let me ask if there are any questions at this point before moving on. Okay. Good. So first, an appetizer. The appetizer is an integrated correlator studied, to my knowledge, first by these authors here in the large N context, and more recently in a beautiful paper by Doragoni, Green, and Wen from a little over a year ago. So what is this object, Gn of tau? It's a space-time integral of the dynamical part of the 20' 4-point function, which I'm calling Tn, against some measure which preserves supersymmetry. This is simple, it's known, I'm not writing it down. And there's an equivalent definition of this object in terms of some derivatives of a mass-deformed free energy on the 4 sphere. That can, of course, be computed by localization. And so this object is determined in terms of this n-1 dimensional matrix integral and derivatives thereof. What's remarkable about this Doragoni et al. Paper is that they conjectured an expression for all n and tau for this object, which is very compact and doesn't grow with n and looks very nice. So what is this expression? It's a lattice integral. You see there's a lattice sum and a one-dimensional integral over xi and some exponential factor and some kernel bn of xi. Now this kernel is a rational function. For example, for SU2, it's just this. For SUN, the degrees of the numerator and denominator grow. So it's 2n-1 and 2n+1 respectively. And this object is manifestly SO2Z invariant because of this lattice sum. And the final thing about it that one would be remiss to not to mention is that different values of n are related by a remarkable what they call Laplace difference equation. Acting with the Laplacian on the left can be related to a linear combination of this object on the right with n values shifted up and down by 1. So this is a beautiful equation, and that allows you to determine these bn's by recursion by applying this, given the SU2 result and the fact that the n equals 1 theory is trivial. For our purposes, there's another formal representation which is useful, which is as a constant plus a sum of an infinite number of these Eisenstein series with positive integer indices. And the sum end is just given for the SU2 case by this quartic polynomial, and for SUN, higher order polynomials determined by recursion, just plugging this into this essentially. So I think this is a remarkable formula, and it raised many questions when I read the paper, sort of where it comes from, what its meaning is, what this function is physically, and so we'll answer some of these questions with our techniques. The deepest thing about it, I'd say, is this Laplace difference equation. We don't have anything to say about that. That is an open question I think we should all think about. So the claim is that this same object, the integrated correlator, is given exactly by the following spectral decomposition. There's a constant piece, and there's the spectral integral over the Eisenstein part, where the integrand is the same coefficients CSN that were appearing here, with a pi over sine pi s factor. Now you look at this and you might say, oh, I see how you can get back the previous formula. You just do a contour deformation. That's correct, except this formula is convergent for all values of tau in the upper half plane and fits nicely into the spectral formalism. And the claim is that this is exactly the answer, equivalent to the lattice integral representation on the previous slide. There are two obvious things about this in the context of what I've said already. The first is that the cusp forms are absent. The second is that the ensemble average is easily read off from this first term. It's just n-1 over 4. And we'll return to this integrated correlator a couple more times just to give a concrete application of some of the abstract things we'll be saying. Okay, so back to understanding the general analytic structure of observables. The obvious questions are, well, we should start with perturbation theory. So first, how does recoupling perturbation theory work in the spectral language? Notice that perturbation theory is insensitive to the cusp forms because they decay exponentially at large y, which is small g. And secondly, how does perturbation theory then in turn constrain the overlap? I've written the zero mode, which is the only one we need to care about because non-zero modes decay exponentially and perturbatively in small g. So I've just rewritten the zero mode explicitly here, right? I've just plugged in the zero mode for the Eisenstein series. And so it seems clear from this how to develop perturbation theory. You just deform the zero mode integral to the left, right? We're going to large y. And so the overlap must have some appropriate series of poles to the left of real s equals a half to give us the perturbative series. The asymptotics of this series will be encoded in the large S asymptotics of the overlap. So in particular, whether it's convergent, divergent, etc., that's encoded in the asymptotics of this overlap function. And as follows from what I just said, if we want perturbation theory to look like it has to look, which is to say, to generate only positive powers of g squared and no logarithms, then the form of the overlap is highly constrained indeed. The most general form of the overlap for observables with the sensible perturbative expansion is given by the following. We insert an explicit factor of this 1 over sine pi s to generate the poles necessary at integer values of s, thus giving us the integer powers of g squared. This s1 minus s is there just for convenience. And there's a function fp of s. Okay, the values of this function on the poles here encode the recoupling data of the observable in question. To this, you can add some regular function, or as we'll see, pretty much regular function, fnp, where the subscript is meant to denote non-perturbative. This function can contribute to non-perturbative corrections at large y, that is to say, instanton, anti-instanton corrections, which go like e to the minus 4 pi n y, right, where n is just going to be some integer. So all the poles are here for perturbation theory, and then if there are possible non-perturbative effects, those are encoded here. Now, just by thinking along these lines, you could constrain these analyticity properties even further. So the first obvious thing is that because the left-hand side is reflection symmetric, that is to say, even under s goes to 1 minus s, so are these functions fp and fnp. These functions have to be real for s on the real line, else the perturbative data would not be real. And it turns out that they have to be regular everywhere in the complex S plane, except for possible poles at 0 and 1, which, when added together, have to actually conspire to cancel, because at s equals 0, this gives the ensemble average, which is finite. Okay. So for instance, if one of them vanishes, then the other function actually has to be an entire function. Okay, and the asymptotic encoding of the perturbative data can be nicely seen here. So if I just say that there's a large y expansion with coefficients Cn, then the Cn's are related to the values of this function fp in this following way, where this completed Riemann zeta function snuck in there, which is just right coming from here. Okay, and remember that this thing is proportional to gamma of its argument. So there's a gamma of n plus a half here. That'll be relevant in a moment when we talk about Borel summability. So let's revisit the integrated correlator in this language, just to give an example. The cusp form overlap was 0, and we see also that the non-perturbative part was 0. Not only that, but for SUN, or for SU2, that is, the perturbative part is just 2s minus 1 squared, this very simple polynomial. And actually, it's the simplest possible thing you could write down in SU2 n equals 4 super Yang-Mills. And by simplest, I mean, in a non-controversial way. So first of all, 2 of the 3 functions that are there are 0. The 2 that are allowed to be 0 are 0. The remaining perturbative piece, in conjunction with the analyticity constraints I mentioned before, must be a non-constant entire even function of s minus a half. What is the simplest such function? It's a polynomial, in fact, the degree 2 monomial. And this thing doesn't depend on any other variables, so it's just a function of s. So up to an overall constant, this is just the simplest thing you could possibly write down, consistent with an SL2Z invariant perturbation theory. So other functions, other observables, for example, the octagon or n equals 8 supergravity, have laid claim to being the simplest observable or the simplest theory. Those are more complex beasts. Here I'm talking about something that perhaps is too simple for some, but it really, I'd say, the simplicity comes through quite a bit in the spectral formulation as compared to the original formulas of Doragoni et al. Okay, so good. Good. So we had these formulas in the previous slide about how perturbation theory looks in the spectral language. And it's often the case that perturbative observables in n equals 4 are not convergent, and they are often Borel summable. If we define what we call the SL2Z Borel transform, this is something that is tailored, it's a modified Borel transform that is tailored to the SL2Z invariant setting. So instead of dividing the expansion coefficients just by a gamma function, which is what one normally does for the standard Borel transform, if you divide by this completed Riemann zeta function, which appends a power of pi and a Riemann zeta, then it turns out that this leads to some very clean results. So first of all, this manifestly respects the SL2Z invariance in the sense that it's dividing by this universal factor that appears as a result of SL2Z. And it can be nicely inverted to give the resummation of the original function using the fact that this completed zeta is actually just the Mellin transform of the Jacobi theta function. This object obeys various nice properties that follow from SL2Z ultimately. For example, it obeys a reflection or inversion symmetry. It has to vanish at s equals a half for reasons I didn't quite explain. Excuse this notation, which I also didn't explain. And we note that the ensemble average is just simply written in terms of an integral of this Borel transform. I want to just point out a little question that this brings up, which is we note that this vanishing implies that this Borel transform has to have a 0 somewhere. And I don't know why. And generally speaking, the physics of Borel zeros is not so well understood. There's a nice paper by Masazumi Honda in the context of 3D n equals 2 theories, which proposes some explanation for this in certain cases. But I just raised this as a feature of these observables, which I'd like to understand better physically. Okay, so end side remark. So why did I introduce this? Well, I'm going to tell you two interesting results about instanton physics, and then we're going to transition to the large N setting. So recall this claim that k greater than 0 instanton physics is determined by k equals 0, the modulo cusp forms. So for now, let's turn off the cusp forms and just imagine that we have the 0 mode, we leverage it into the overlap for the Eisenstein series, and then we get all the other non-zero modes just by plugging in the non-zero modes of the Eisenstein series, where this is now known. Naively, this suggests that if the 0 mode has a Borel summable perturbative series, then the non-zero modes do too. After all, the latter are determined by the former. But it turns out this isn't quite obvious because of the different functional dependence of the Fourier modes in Y. Right? The 0 mode of the Eisenstein series, which is the sum of two powers, the non-zero mode involves Bessel functions. But you can prove this, and it leads to a really nice relation between the radii of convergence of the Borel transforms in the different instanton sectors. If I define R as the radius of convergence in the 0 instanton sector, and Rk as the radius of convergence in the k instanton sector, where I'm defining these radii as the radii of the SL2Z Borel transforms, which I introduced before, then their relation is just this boxed relation, which is extremely simple. And I want to mention this in the context of general resurgence in CFT and QFT. It's a much stronger result than one usually gets. Usually, resurgence allows you to resum effects in a fixed instanton sector and reconstruct non-perturbative instanton, anti-instanton corrections in that fixed instanton sector. What we're seeing here is that the different instanton sectors are related, and the asymptotics are related in this very clean way, which would be nice to understand from different perspectives. One more formal result that'll sort of seem sort of random, but hopefully the next slide will bring it all together. If again the cusp form overlap vanishes, then you can actually reconstruct an observable O as a Poincare sum over its zero mode. So this again is manifestly SL2Z invariant. It has to be equivalent to the spectral decomposition once you get the normalization right to match the zero mode. And it looks like this. After some massaging, you can write it in terms of this SL2Z Borel transform as follows. And hopefully now it's obvious why I mentioned this, because this looks exactly like the form for the integrated correlator that we found previously. So we've now derived the form of the DGW formula for the integrated correlator. It's just the Poincare series representation of this observable, where this kernel Bn is the SL2Z transform of the zero mode. Those authors observed these three properties of this function. Empirically, we're seeing here that it follows from SL2Z in this very universal way. And again, this formula we now understand is equivalent to the spectral decomposition, but it's a bit more complicated than it, involving a lattice and a one-dimensional integral instead of just this one-dimensional integral. Finally, you can check this k-instanton result that I mentioned previously involving the radii. How is this realized for the integrated correlator? Well, it's kind of cute. From explicit expressions for this thing, for example, as determined by localization, you can read off that in the zero instanton sector, the radius is 1. So here I'm fixing SU2 for simplicity. So our prediction is that Rk, the radius of convergence in the k-instanton sector, is just 1 plus k squared. And that actually is true. And it's just the solution to this equation. You turn out to have to maximize p plus q squared over p and q subject to these conditions, which is just 1 plus k squared. So it's a very nice confirmation of that general formula. Okay, so I've said a lot. We haven't gotten to large N, but just to summarize, we've introduced the main tool, which is the spectral decomposition, and then some little tools along the way, which revealed some of the finer structure of these n equals 4 observables and shed some new light on the integrated correlator. Are there any questions?
Actually, can I ask a question?
Yes.
So this result for SU2 where you didn't have non-perturbative, is that also going to be true for higher N, or just that's just
Yes.
special for SU2?
For all N.
Okay.
Yeah, let me go back here. What's special for SU2 is that the perturbative part is just this quadratic monomial.
Okay, but
The higher guys are determined by this recursion relation. So recall this Laplace difference equation. When it turns out this implies a recursion for these C's, in a recursion in N. So in particular, this is quartic. For N equals 3, it's going to be sextic. It always goes up by 2. And so the same will therefore be true of this FP function.
I see. Okay. So can I then also ask, so in a sense, is this because this integrated correlator is basically coming from the partition function on S4? And then when you go to the limit where the mass goes to 0, that all the instantons disappear?
I don't think it's that simple because there are other observables you can extract from this, which don't have this property.
Okay. All right. Thanks.
Sure. We talk in our paper about what you might call the other integrated correlator. If you take 4 mass derivatives and set mass to 0, then you get an integrated correlator with a different measure. That thing is much more complicated for reasons I don't understand. And that has non-perturbative pieces and cusp form overlap.
Okay. All right. Thanks.
Yeah, sure. Okay. Good. So large N will be sort of hopefully concise, and then that'll let us transition to supergravity. And time-wise, I have how much time, Abel?
You have 15 more minutes.
Great. Okay. So we're going to work on the TÜV limit. As we all know, you can develop a genus expansion for n equals 4 observables. Not all of them, but a wide class of them. And that's a statement about the zero mode, because the non-zero modes are exponentially suppressed in n. So one can develop this genus expansion of the zero mode with functions of lambda multiplying each power of n. So from here, to develop the genus expansion, the algorithm is clear. First, and mainly, you understand how the overlap admits a 1/n expansion. And then you just plug in, you trade y for n and lambda, and then you plug these things in and see what you get. Now, the argument for the scaling of the overlap with n is rather straightforward. I won't give it, but it leads to the following formula. Okay. Now, I'm suppressing coefficients, and I'm turning off FNP, the non-perturbative part of the overlap. We'll see it reappear in a moment. So there's the constant term, there's the sum over genera, there's this universal piece of the overlap that we introduced before. Here's this genus G part of the perturbative data. And there are two terms, each coming from the zero mode of the Eisenstein series. Now, the first term looks normal, looks good. This is going to give us the usual lambda dependence at genus G of whatever observable we're looking at. But it comes with an SL2Z partner, and it turns out that there's an explicit power of n appearing here with a 1 to the 1 minus 2s power. Okay. This must appear due to SL2Z. We're just rewriting the spectral decomposition in this limit. But it might at first seem a little strange that you're getting extra powers of n at some fixed genus G. In order for this to be consistent with the genus expansion, well, what has to be true? At large n, we need to develop the large n expansion of this thing, we need to deform this contour to the right for the second term, thus picking up negative powers of n. And so the poles of this have to be at half integer values of s, otherwise you'd get powers of n, which are inconsistent with the total genus expansion for this observable. So that tells us something. Because this function fpg 1 minus s also determines the location of the powers of lambda at large lambda, where we also would deform the contour to the right. The strong coupling expansion is only a odd half integer unless FNP is 0. That is to say, if you find an integer power of 1 over lambda in some observable, that means that there must be some other effect here, and it therefore must come from the non-perturbative piece of the overlap. So this gives a nice diagnostic for when you have non-perturbative effects in your observable. And again, non-perturbative here means e to the minus y type effects, where y is 1 over g squared. The second thing already alluded to is that SL2Z seems to rearrange the 1 over n expansion. At large lambda, for example, you're going to get whatever you get from here, so the usual sum in powers of 1 over lambda, but you're also going to get these extra terms which seem to be associated with some fixed genus, say genus 0. You should think of these as renormalization terms. Notice they come with positive powers of lambda, and so these are the terms that cut off the large n, the 1 over n expansion at large lambda with the string scale. So in bulk terms, if you do loop corrections in supergravity, there are some divergences which the string scale cuts off, and these are just the field theory translation of those terms. What's interesting about SL2Z is that it seems to associate these terms with lower genus rather than collecting all of the terms of a fixed power of n and calling that, genus G. More can be said here, and I'd like to understand this in greater detail. But for the moment, let's move on and just state that as something interesting. And the last thing that follows from this, I think also hopefully will be obvious. If you have non-perturbative effects at large lambda, then you also have non-perturbative effects at large n, that is to say, e to the minus n effects. Well, why is that? Non-perturbative effects will come from the asymptotics of this function at large s, where you deform this thing to the right. So you deform the contour to the right, and you see if the series diverges and you need non-perturbative corrections. Well, the same will be true applied to this term as well, but those corrections will be non-perturbative in n at some fixed lambda. To summarize the situation, if you have non-perturbative effects at large lambda in powers of a non-perturbative scale given by e to the minus root lambda, which one can show as characteristic in n equals 4 in situations where these effects exist, then S-duality tells you that there is an S-dual scale in terms of what you might call the S-dual coupling, which is just n over g squared, that is to say n squared over lambda. And these effects must come along for the ride too. What are these in the bulk? These are F-string worldsheet instantons, and these would just be, therefore, D-string worldsheet instantons. So SL2Z ties their existence together in a nice way. Okay, so now on to supergravity and ensemble averaging, and we've got about 10 minutes, so we'll get to some of this material, most of it, I think. So the punchline might already have been visible from this equation. Okay, notice that at large lambda and large n, this entire second term is suppressed compared to this. Okay. So if we include FNP, generalizing the previous equation, you can show that the same observation holds. So for concreteness, suppose we look at the order n squared piece of some observable O. Then the large lambda expansion can be developed. There are the terms suppressed by powers of lambda with some coefficients. And what survives here is the leading piece of the average. So this average is a function of n. In the large n limit, what survives is the leading large n piece of this, which I've denoted as a double bracket. Now this looks a lot like what we usually do when we expand at large lambda, except the infinite lambda answer is the large n limit of the average. So you immediately infer that these two things are equivalent. And we can, of course, invoke the usual equivalence between the strong coupling planar n equals 4 theory and supergravity to phrase it this way. There's an extension of this to all orders in 1 over n using the genus expansion that I wrote previously. If you define the large n limit of the genus G part of the average with this double bracket in this way, then the strong coupling expansion takes the following form as a sum over genera. There's the leading large n piece of the genus G average, and then there's stuff that's suppressed either in n or in lambda. So there's a genus G version of this statement, which is also interesting, but not being the main point of this talk. Let me move on to try to give a better understanding of what exactly is going on in this equivalence. So here's a possibly useful way to think about it. If you take fixed tau and large n instead of the TÜV limit, the leading order large n behavior is just supergravity. And the tau dependence appears in the subleading terms in n. So if supergravity term is order n squared in my conventions, then you're going to get terms starting at root n and decreasing in half integer powers of n times functions of tau. What this suggests is that to leading order in 1 over n, in other words, dropping these terms, the average just gives supergravity back because you're averaging something which doesn't depend on tau. So if you normalize the average, then the average will just give 1 and therefore give you back supergravity. Now that's intuitively true, as we showed, but this argument doesn't actually literally work. And the reason is that these functions are not square integrable. You can't average the 1 over n expansion. That is to say, the 1 over n expansion and the average don't commute. So at large y, these functions go like a positive power of y. And so we can't compute their average, it diverges. So the calculation is not controlled. If you imagine trying to regularize it, then you still don't get the right answer because the n dependence is not correct. So this goes like n squared. And if you remember before, the integrated correlator, the subleading term in the average was order n, but here the next term is order root n. So you can try to regularize using some standard methods, but that doesn't give you the right answer. So what our calculation does is that it confirms this intuition rigorously, and by working in the TÜV limit, extends the correspondence to higher orders in 1 over n in the process. So some comments. The traditional holographic correspondence still holds. I want to make that clear. We're not saying that it's really only the ensemble average n equals 4 theory, which is dual to string theory. It's just that there's an equivalence between the strongly coupled theory and the average at large n. And this averaging generates a simple bulk dual, indeed the extremal theory consistent with the symmetries involved. It also suggests a plausible, arguably, new strategy for deriving ADS5 supergravity from CFT, which is to compute large n limits of averages instead of large lambda limits of planar quantities. So if you had some theory of averaged n equals 4 observables, In other words, if you could reliably compute averaged observables, then you just take their large n limits, and that's equivalent to knowing the function as a function of lambda and taking the large lambda limit. It's possible that this can be done in part because of inspiration from some recent developments in array CFTs in 2 dimensions, where the average spectral gap at large central charge has been derived, but not by scanning over the space of theories, which is not practically possible. So it'd be nice if this were true, obviously, this sort of theory of averages I'm dreaming about, maybe something to shoot for.
Eric?
Yes.
I have a question. So you have 3 different computation of this finite part in an equal for this maximally symmetric theory. Is there room for these things to have not be the same?
Is there room?
Or can it be just an accident of having the fact that it's maximally symmetric is the nicest context where you could compute these things? Could these things not be the same? Could these constant terms not be the same?
Well, let's see. It sounds like you're alluding to whether some generalization of this to situations with less symmetry might hold, and whether that actually, or whether
that would be, I guess, that would be a check ultimately if you compute it in n equal to 2 theories where you also have S-dualities. You know, would they all match?
I don't think it would be
a harder question, but at this level, I guess I was hoping to see whether there is a way you could see that these things could not be the same. The ensemble average, the supergravity result, and
yeah, I certainly think that. I mean, before doing the calculation, I think there's no a priori reason to think of them as having to be the same in any rigorous way. I think if you extended it to theories of less supersymmetry, it wouldn't be a check of what we're saying. It would just be a different generalization, a check of whether this is a more general story in ADS-CFT. Let me actually transition exactly to that question, if I may. So this is my next slide. Let's imagine that we have some other theory of the conformal manifold M, a multi-dimensional one. Perhaps there's a generalized S-duality group S, and suppose there's some coupling G, which in a TÜV type limit takes you out to some gravity regime. And in this regime, there would be other moduli which are not along the quote unquote gravity direction, but which are part of the theory and in the bulk are furnish some bulk moduli space. The suggestion of our work is that automorphic averages over S-duality groups, or more generally, certain ensemble averages over the conformal manifolds, may localize onto supergravity, that is to say, be equivalent to the strongly coupled physics at leading order. So we did not investigate this in any detail. In the paper, we articulated some scenarios which seem plausible. It will be interesting to understand whether any of them is true. And just to demonstrate the scenarios, at least the most sort of mainstream ones, let's use the ADS3 times S3 times T4 holographic duality as an example. This case has 20 moduli. There is an S-duality group. And at large central charge, there's a TÜV type coupling lambda, which interpolates out to supergravity along a particular direction in moduli space, which I've called G. See here at the central charge. So what average could lead to a supergravity theory? Well, there are 2 broad types of possibilities that I see. One is to average over the entire conformal manifold with respect to some measure. And the second is to average only over the gravity direction with respect to some measure. Note that in the first scenario, you're averaging over everything, including the moduli that don't seem to have anything to do with taking you out to supergravity. In other words, in this case, you're also averaging over the bulk. You can nevertheless imagine that the result is a simple theory, and that would be very interesting. But perhaps all you need to do is average only over one direction, the one that's responsible for taking you out to the strong coupling regime relevant for gravity. Maybe that's the generalization of the story we're seeing. Of course, in our case, due to the maximal symmetry involved, these 2 things coincide. Good. So We are short on time, but I'll move toward the end quickly. So this whole story, I think, strongly motivates to study the SL2Z ensemble, that is to say, the space of n=4 theories and the statistics of this space. I think this is an interesting question in CFT, not just in n=4, but more generally. But it has very direct relations to holography and wormholes. Let me just mention some calculations we did, and then we'll go to the end. So the simplest thing one can compute is the 2-point correlation in the moduli space, aka the variance, which I've drawn schematically here. Okay, we can define this. So the variance is defined as the average of some observable O squared minus the average of O squared. And this is just the average of something you call O spec squared, where O spec is just the difference of O with its average. Now, it turns out that this has a very nice expression in spectral space. The variance is just, up to a normalization, equal to the second moment in spectral space. So take the overlaps, square them, and integrate them. So the second moment in tau space, which is what the variance is equal to the second moment in spectral space. So that's a very nice correspondence. And it turns out that this thing is not so hard to compute, at least when the cusp form overlap vanishes. So I'll say two things about this. At large n, the leading term is down by 1/n compared to the squared average. It's a bit strange that it's 1/n, 1/n squared. I'll maybe make another remark about that in a moment. But the formula is very simple. And we can check this against the integrated correlator. So for the integrated correlator, this quantity is given by this nice Riemann zeta integrand. You can do this integral numerically. If you can do it analytically, let me know. You get this answer. And we can plot this on here as this dotted line and check it against direct evaluation of the variance for finite values of n, starting at n=2 and going out to n=107, I believe. And as you can see, this provides a nice check of not just the coefficient, not just the n³ scaling, but also of the coefficient. So this has bearing on whether there is a role for wormholes in higher dimensions. The short answer, and because I'll conclude instead of saying everything that can be said here, is that it raises more questions than answers, but it comes to bear on the factorization puzzle that is now in vogue in higher dimensional ADS-CFT. So let me state the puzzle. I think it's important to state it carefully. To my mind, there are two parts of the puzzle. On the boundary, the puzzle is, in a product of observables in two decoupled CFTs, why is there a contribution that appears to correlate them? And when and for which observables and how does this happen? On the bulk side, the question is, how do wormholes, which seem to exist, conspire with other bulk ingredients in a UV complete theory to restore factorization? The second formulation is a puzzle for the semi-classical theory. How does the UV completeness of the full theory, say string theory, trickle down to the semi-classical theory? And I just want to say this is not a paradox because we don't have sufficient control over the bulk path integral to be confident enough that we know the full solution space, but it is indeed an interesting puzzle. And this equivalence that we're finding suggests there's some gravitational manifestation of these statistics. But how much does the bulk string theory know about these statistics is an interesting and somewhat confusing question. We make some comments about this. And in light of time, let me simply skip ahead because I don't want to abuse the clock. But we can discuss this in discussion if desired. So here's a summary of the talk. And there are lots of future directions that I'm excited about. Some involve trying to adapt the bootstrap and combine it with this technology. For example, bootstrapping thermal correlators or just 4-point functions in this language. Extensions to other S-Duality groups would, of course, be profitable. These groups are especially ripe for it, and they appear in the context of non-simply laced n=4, but also certain other SQCD theories. I think there's some nice stuff to say there. And these more general questions also deserve some attention, but let me just stop and take questions. So thanks.
Okay, let's thank Eric for the nice talk. If you have a question, just go ahead and unmute yourself.
Hi, Eric. Really interesting. I
Thanks.
was wondering if you could just say, with the harmonic analysis for other S-duality groups, we have the mathematicians kind of built up the toolbox there, or is that?
Yeah, that's the question. So there's a limited number of cases where I know that they have. There may well be cases that I don't know, but where they have. But the Hecke triangle groups are a case where they have. And basically, there are so-called arithmetic and non-arithmetic triangle groups. And in both cases, this decomposition exists and is very simple, nicely related to the SL2Z decomposition. Another natural thing to ask about are congruent subgroups of SL2Z.
Right.
And for those, I have incomplete knowledge of what is known, but absolutely some is known. Beyond that, it seems like more is unknown than known. Yeah, so for example, for SP2G, Z, it's not known in general. Yeah, so, but I think more can be done. But for the S-duality groups that appear in SCFTs that can be large and complicated, I think in general the mathematicians don't have the framework in place for that.
Okay, thanks.
Question? I have a question. So here you were just studying averaging over S-duality. What about, let's say I tried to average over conformal manifold?
You mean changing the measure?
Yeah, over the conformal manifold of the theory instead of the S-duality group.
Well, in my mind, that's just, sorry, in this context, that would just be changing the measure. So, I mean, well, so one could do that. The spectral decomposition that we're using, for SL2Z relies on using this natural Peterson inner product. And of course, because the homological metric coincides with the Poincare metric, this is natural from every point of view. For these like super QCD theories where those two things are not the same anymore, I don't know how to define the ensemble average with respect to the Zamolodchikov metric because I don't know the Zamolodchikov metric except in implicit form of a matrix integral, right? So even though there's an SL2Z in that context, it's I would only know how to sort of write things in terms of the automorphic average. But it's a good question. Yeah.
We can stop the recording and then people can have a